Armed with the tools and the insights that symmetry provides, we're now ready to take a look at butadiene and how one might treat its quantum mechanical states for the pi system of the molecule. Now, we know that Huckel theory provides one set of approximations and simplifications that make this an easier problem, but let's see what symmetry theory gives us. Remember that whenever we have some set of functions, and I'll just call them psi sub I, that are basically basis functions for evaluating a quantum mechanical system, that this results in a secular equation that looks something like this, where we've got a Hamiltonian matrix minus E times a overlap matrix, and that this secular determinant must be set equal to 0 and solved for the energy levels for the system. All right, so this is the general problem, and in general it would produce a matrix, or a determinant, I guess I should say, that has these kinds of elements, H22 minus ES22, H12 minus ES12, H21 minus ES21, and so forth. Okay, basically every element in this large determinant would have some number in it, and we would set that equal to 0. So this could be a massive problem, depending upon the size of the basis that we're using, but it's a large problem, and it's the thing that the Huckel theory was trying to simplify by introducing these sort of simplifying approximations, which resulted in a secular determinant that at least had some zeros. It only has, 3 diagonals in the matrix that have non-zero elements. What does symmetry do for us, though? All right, what I want to do is talk about the symmetry-adapted functions that we've generated in earlier videos that correspond, for example, to AU symmetry and BG symmetry under the C2H point group. So what these were, I'll remind you, is phi1 plus phi4, phi2 plus phi3 for the AU symmetry functions, and phi1 minus phi4 and phi2 minus phi3 for the BG functions. All right, so these are the 4 basis functions, and I will just simply line these up as psi1, psi2. I'm going to actually call this one psi4 and this one psi3, and see how these generate a secular determinant. All right, now we know that when these functions belong to different symmetries, that their overlap integrals and their Hamiltonian integrals will be 0. So what does that mean for the form of the secular determinant? Well, if I know that, for example, phi1, phi3, psi1, psi3 is equal to 0 because they're of different symmetry, that means also psi1, psi4 will be 0, psi2, psi3 will be 0, and psi2, psi4 will be 0. So lots of things, I'll just say, and others will be 0. This will also be true for the Hamiltonian elements. All right, well, if both the Hamiltonian element and the overlap element in a particular block of this secular determinant are 0, then that greatly reduces the scale of this problem. So, for example, I'll have these elements that will still be non-zero, potentially. Okay, up here, but they will be in effect separated from the other half of the secular determinant, where I'll have these elements. And everything in here and everything in here will be zeros. So this has greatly reduced the complexity of this problem. Now, this is a pretty simple case, and I've only got 4 basis functions, but imagine if I'm dealing with a problem where I need, 100 basis functions. I've got a 100 by 100 matrix. That's a 100 by 100 determinant that I would need to evaluate in order to solve for the energy levels. So it's a much bigger problem than doing, say, 250, but 250 by 50 determinants. However, it's even better than that, because a lot of times what happens is we have irreducible representations that produce even smaller blocks than this, and each one becomes an individual problem that we can solve separately in order to find the energy levels of a system. So this, the Huckel theory approach results in several zeros in here, but not block diagonal. And because it's not block diagonal, this means that ultimately the equation we need to solve is a quartic equation, that it has terms that have e to the fourth and e cubed and so forth equal to 0. Whereas this one now has only two quadratic equations that need to be solved, because it's two 2 by 2 blocks of this Hamiltonian. So this is something that's actually much easier to solve than this, although admittedly, and with a degree of a dimension of 4, it's not going to be difficult to solve under other circumstances. But the whole point, though, of this exercise is to say that when we can use symmetry, we can greatly simplify the secular determinant and cause it to be block diagonal, and each block can be solved individually and separately from all of the others in order to get the results for the system.